What's good, y'all? Welcome back. It's Jeff. In this video, we're going to discuss two definitions that are really important in circuit analysis. Those definitions include parallel circuits and series circuits. We are also going to look at some specific examples that we've already seen in our previous analysis and filter those examples through these new definitions. One of my themes in applied linear algebra is to filter theory through applications. As we develop a bunch of different examples, we're going to return to those examples numerous times to highlight very, very special theoretical results through the lens of practical measurements. I find this to be one of the most powerful critical thinking skills, and you'll see that at play in this video. Parallel circuits are a special type of circuit that arise in circuit analysis, and in a parallel circuit, we say that there are exactly two nodes of that circuit. The general canonical easiest version of a parallel circuit will take this form. In this case, I'm replacing specific circuit elements with a generalization. These boxes could be resistors, they could be DC voltage sources, they could be DC current sources. We've also seen an example, which we'll cover again in 1 second, that this could be a multimeter. The point of the matter, though, is that when we look on either side of this, these elements are connected by only one piece of wire on one side of the body and a second piece of wire on the other side of the body. Now, some of you might be very astute and say, what do you mean one piece of wire? We'll take a look at what that looks like in the actual breadboards. But what we say is that the segment of conductor highlighted in blue above is a single node, and the segment of conductor highlighted in orange below is a single node. Check it out. The element bodies are stuck in between those two nodes. This is a circuit where there is only two nodes. A level up from that would be to add an additional element. Notice though, when we add this additional element, we haven't changed the topology of the circuit in terms of how many nodes connect this. Indeed, we have a single node highlighted in orange on the bottom, and we also have a single node highlighted in blue on top. These elements are in parallel. One kind of nice intuition that I like to think about is if we look at the actual bodies, they actually look like they're next to each other, like cars parked in a lot. They're literally parallel to each other, not following each other. Same thing over here. These are parallel. Let's take a look at where these parallel circuits have arisen in our previous work to understand circuits. The first location that we saw this was when we were learning how to measure voltages with a voltmeter. In this case, we see that we have a voltage source, a resistor, and then we connect our voltmeter, aka the digital voltmeter, the digital multimeter, in parallel with that circuit. So notice, if I were to erase these element bodies, we have a single node up top, which is highlighted by this blue. All of that wire is a single piece of wire from the standpoint of electron flow. And then we have a single node on the bottom. And that is why we say that when we take voltage measurements, we do so in parallel. Let's take a look at another example of where we've seen parallel circuits arise in our own measurements. In example 5 in our YouTube videos, we actually built this circuit, which had a single DC voltage source connected with the positive lead on the bottom and the negative lead on top. And then we had two resistors in parallel. This indeed follows that definition because there's only two nodes in the same structure. So notice, even though the actual bodies of the elements are not the same, the topology, the connectivity, the way those elements are connected maintains this really kind of powerful property of parallelity. Let's get real specific about what we mean when we say two nodes in practice. Here was our example 5 circuit. We did this measurement in one of our previous videos. This is how we actually built this circuit on a breadboard. We had our single voltage source, we had two resistors in parallel, and we connected them here. What I wanted to show you on this side is this is the breadboard that I actually disconnected and deassembled. And take a look at this. When I look at how these are connected on the back of the breadboard, the internal function of this circuit that you see is replicated right here. So when we connect this resistor to inside the breadboard. When we push it in, it actually goes into that contact strip. The moment that happened, the top metal lead of this resistor becomes electrically connected to the metal in the contact strip. So from the standpoint of electron flow, or as an electrical engineer would say it, from the standpoint of current, there is absolutely no difference between the metal on this resistor and the metal in the contact strip. They're connected, and electrons can jump between them without any issue. Same thing over here. The contact strip is connected to this jumper wire. Flow of current happens with no change in behavior. Connects to this contact strip, comes down, connects to this metal piece on the resistor. So this whole set of metal is one node. That's what we see at the top of this circuit diagram. The blue node highlighted in the ideal schematic represents the concept that all of this metal is electrically connected and no changes in current flow happen as a result of this, at least on the scale that we're looking at. Same thing's true on the bottom. There's a single piece of metal happening inside this breadboard. So this lead connects to the contact strip, connects to the jumper, connects to the other contact strip, connects to that bottom lead of the other resistor. When we connect this voltage source across, what we see is the actual wire inside this insulation becomes electrically connected to the whole thing, and that's why we say that they are in parallel and there's only two nodes. We're going to avoid doing this type of deconstruction in the future, but I do think it's super useful to get a sense of what's happening with the nodes in terms of the actual internal workings of these breadboards and what's happening when we connect the leads of our individual components through the contact strips. Let's move on to the next definition, which we're going to call a series circuit. This is also a special type of circuit that arises in circuit analysis. We say that in a series circuit, each lead of a single element makes only one connection to a single other lead of a different element. Let's take a look at what this means in practice. Here we have a 3-element circuit. We're not specifying the exact type of element, so I'm just going to call the element label X as a variable. We're not really specifying that. X1 is the first element, X2 is the second element, X3 is the third element. Notice that the top lead of X1 makes a single connection with this left lead of X2. That connection is the only connection for that lead. So that forms a node, but there's no other leads from any other elements coming out of that. In other words, each lead is connected to only one other lead. At least that's true in this node. If we look at the other side of the body of X2, here we've got the second lead. It makes a connection with the first lead of X3. That's the only connection there. And at the bottom, the same thing. Here we have a single node. That connection is only between those two leads. Nothing else comes out of that. Now, another way to think about this that is going to get into graph theory, we're going to develop this really strong connection between graph theory and linear algebra, and then the topology, the connectivity of our circuits. It's kind of unique to my approach to this. I've not seen this done very well in any of the engineering literature. When we go ahead and draw a path around this circuit, so imagine traveling around this particular circuit, we say that there's only one path. So there's no other way that I can move around these elements except for going through X2, X3, X1. I can't get around it. Let's take a look at yet another way that this might show up. One of the things that's really interesting about conductors, we will see this in a future video, is we don't really care about the size or shape. So in particular, I could take this X3 element and kind of just mold it down to the bottom there. So literally I'm just like shrinking the orange bit, which would extend maybe the blue bit, and I can bend them in any ways. It doesn't change the behavior. This is in series because if we look at the connectivity between the leads, each individual lead of the elements is only connected to a single lead of another element. Another way to think about this same exact circuit, these leads connect only once. There's only one path around the circuit, assuming we don't take direction. That's called an undirected path. We'll talk more about that when we discuss graph theory. But we say that these three circuits represent series circuits. Let's take a look at some examples of work we've already done that highlight series circuit. For example, when we took current measurements using an ammeter, we disconnected one lead from the circuit, inserted our ammeter in series so that the single lead of disconnected lead connected to one of the probe of the ammeter, and the current actually ran through the ammeter as a way to measure. Notice that's in the same form in series. Another example that we saw was when we had a voltage source in series with resistors. Another flavor would be we could actually take the voltage source out and replace it with a current source. Doesn't matter the actual element body or the behavior. What matters is the topology, the connectivity. Each lead of these sources connects to only one lead of another source. When we have a circuit like that, we call it in series. Let's take this one step further. We can have series circuits with 4 elements. In that situation, we would have this closed path. There's only one way to get around the circuit. Another way to say that is every lead connects to only one other lead. There's a series circuit. Here's yet another version where we replace the DC current source with a DC voltage source. Still, those are in series. That concludes our introduction to parallel and series elements. Let's do a quick recap. Parallel, we're thinking about them literally right next to each other in parallel. Series, we're thinking about them back to back, chained together so that only one lead connects to another lead. We will not focus heavily on parallel circuits and series circuits in terms of developing the linear algebraic nodal analysis algorithm. We will also not go deep into Thevenin and Norton's equivalent circuits. The point of introducing this is just to develop some of the basic ideas that may be helpful later when we're talking about what happens with the linear algebraic construction in terms of standard terminology that an electrical engineer would like to see. In the next video, we'll further refine our ability to talk about ideal diagrams. I'll see you in the next video.